Okay, so day 3 is definitely the hardest stuff you'll see in circuits. Day 4, we're looking at something called EMF and terminal voltage. So basically, what this is to do with batteries. So battery, to break it down, like something like the following: we have electrodes. Just picture like a battery. So that's a very simplistic version of a battery. Okay, so basically how a battery works is you have some positive electrode and you have some negative electrode, and inside we have something called an electrolyte. So because there's a charge difference, electrons are going to travel through the electrolyte from one side to the other. So this is how we create that potential difference. So on one side we'll have 0 volts, the other side will have our whatever volts, or 1.5 volt battery, or 6 volt batteries, just whatever you have. But like everything else in this world, nothing is 100% efficient. So basically, what a battery has what's called an internal resistance inside. So we've drawn batteries in the past to look something like the following. So we have point A and point B, negative and positive. In reality, it's more like this. And if I draw a dotted line to kind of represent this encapsulated within the battery, so we have what's called an internal resistance, this little r, and what do we call the EMF, the electromotive force. So this is the voltage of the battery when there's no electrical device connected to it. If we suddenly attach something to it, the voltage supplied, just say it's a 6 volt battery, when you actually complete a circuit, what you're actually going to get is not 6 points, because this little r is going to consume some of your potential. So you might have a 6 volt battery, but you might only be supplying, say, like 5.8 volts to the load that you attach to it. It's a very simple formula, or what we call the terminal voltage, VAB, or VAB. So that's our terminal voltage after you take into account the internal resistance. Is just equal to our electromotive force. It's just this little, this Greek symbol. I think it's Greek, whatever they use, but this symbol is used for electromotive force minus our current through the circuit multiplied by the resistance, internal resistance. So here's an example. A 12 volt battery has an internal resistance of 0.1 ohms. They're usually very small. If a 10 amp current flows from the battery, what is its terminal voltage? So if we have VAB is equal to the electromotive force minus IR, just plug it in. So the hardest thing with this is remembering you're given the EMF or the terminal voltage, like which one goes where. So it's 10 amps multiplied by 0.1 ohms, and we get 11 volts. We're done. It's pretty straightforward. So if you want to have an idea of what's happening here, more visual representation. So here is our circuit, and I have that internal resistance right there. I'm going to do the dotted line. So it's saying it's a 12 volt battery. So our EMF is 12 volts. Our internal resistance is 0.1 ohms. And the question though is, what is our terminal voltage? So if we know there's 10 amps of current being drawn from it, that means this one is consuming the 1 volt. That means this must be consuming the remainder, so 11 volts. Okay. So we're getting some plus minus like this. So we're gain 12, lose 11, lose 1. Gain 12, lose 11, gain 1. Sorry, lose 1.